Good afternoon to everyone. It is wonderful to see all of you today here. Welcome to a special Viterbi Live webinar today, featuring our school's namesake and benefactor, Dr. Andrew Viterbi. This is quite a unique time in history, and one that calls for a unique discussion about what is happening around us. I tend to think that some of the quantum physicists are right in saying that we live in many universes. Actually, they are advocating a theory of many worlds. Somehow, at the beginning of March, we moved to a different coronavirus universe. Having Dr. Viterbi with us today certainly help us understand why we're here, what we need to do, and how we will get out of this to rejoin perhaps the previous universe in which we used to live. This tongue-of-cheek introduction is to say that we are very fortunate to have with us today Dr. Viterbi, a titan within engineering, and we are very lucky and grateful to have him with us. In fact, we had so many people register for today's presentation that we made a decision to stream the presentation on YouTube to accommodate all viewers. So however you're tuning in, and in whatever modality, we're so glad that you're here part of this important and historic event. Speaking of historic events, I wanted to say that today is a significant day for us for another reason. You see, for all the mathematicians in the room, and Dr. Viterbi, I'm looking at you, you may be familiar with a constant which is known as Euler's constant, or gamma constant, which is 0.57. Even before I knew we were going to have all of our events online, I was already thinking about how to make this day, 5/7, May 7, an International Day of Online Engagement to share all the milestones we have accomplished together in the past year. So earlier today and last night, I visited through Zoom many constituencies of engineering, Viterbi engineering students and alumni around the world, in China, Taiwan, and India, and other places through Zoom to share the same message, that we're a Trojan and Viterbi community that is stronger together, and together we are engineering a better world for all humanity. Andy Viterbi is a great example of this. Through his accomplishments as members of multiple academies, multiple recipient of multiple doctorates, honorary doctorates, a philanthropist and an entrepreneur, co-founder of Qualcomm, and with so many accomplishments that we are so humbled to recite today. Today, he will present the mathematics of epidemics, a century-long saga, giving his unique perspective on the current pandemic. There are few more qualified to do so. Andy earned one of the first doctorates in electrical engineering ever granted at USC and created the Viterbi algorithm, a mathematical formula that eliminates signal interference and allows seamless communications across the world. Simply put, Dr. Viterbi paved the way for the widespread use of cellular technology and wireless communications. Today's meeting is an example of that and forever change the world. As questions come up, please type them into a question and answer box. Dr. Viterbi will answer as many as he can at the end of his presentation, and I will moderate that particular interaction. Now, let's get this going. Please join in a warm welcome for Dr. Andrew Viterbi.
Good morning, all, and thank you, Dean Yortsos, for that introduction. Now, some of you who may know me and my colleague, Roberto Padovani, may wonder what two information theorists and retired wireless engineers know about epidemiology. And the answer is, until almost precisely 2 months ago, we knew nothing. At that time, around Qualcomm, our former company that I've been retired from for about 20 years. There was a email describing some interesting work that was done almost a century ago in 1927, and commenting that the math was too hard to follow. So of course that was a challenge for both me and Roberto. And we kind of egged each other on until we had completely deconstructed the paper and found all the weaknesses and the strengths, especially the strengths. So I will begin by going to my PowerPoint, which is mentioned. Okay. Was based on a paper written in 1927 in the Proceedings of the Royal Society in London by two health science professionals, in fact, British officers who served in the health organization, in public health. We wondered what their background was, and we found that towards the beginning of the 20th century, there was a lot of interest in the mathematics of epidemics. It was started by a gentleman named Ronald Ross, Sir Ronald Ross, who was quite distinguished. He was the second scientist awarded the Nobel Prize in Medicine and Physiology back in 1902 for his discovery of the transmission of malaria by the mosquito. He was also a closet mathematician and published papers in several areas of pure and applied mathematics. Now, interestingly enough, Alfred Nobel, who offered the prize, would almost certainly did not approve of the mathematics. He had forbidden the Swedish Academy from setting up a Nobel Prize for mathematics, and that was for his own particular personal reasons. And at that time, the issue, therefore, was not the mathematics, but the transmission of malaria. He found that the mosquito was the guilty party. Moving on a few years, one of his disciple, Anderson McKendrick, and a disciple of his, excuse me, who was William Kermack, working together in McKendrick's lab, and thinking about I guess in 1927, the Spanish flu of 1918 was very much on their minds. And they found, they actually wrote a very elaborate paper with all sorts of what we would call bells and whistles, but stripped to its basic foundation, it was really a very simple model that they came up with. And that model is shown here, sometimes called the SIR model, for susceptible, infected, and recovered. So think about having 3 rooms with doors that only face the next room over, and it's only possible to move, in this diagram, from left to right. So susceptible means that there's a population, which we also denote as X of t. At time t, there are X people who are in this first state or room, where they are completely healthy, but they are susceptible to the infection. In the second room are the infected, and then as they cure or die, we categorize them together as recovered. They're out of the game, in other words. So susceptible, we call X, infected Y, and recovered Z. Now, in order to get the game started, you have to have somebody get infected. So that comes in at the beginning, and we call that Y naught. Y is the number of people, so a number of people anywhere from 1 to perhaps 10 or 20 go into that room, and now they start their activity, which I'll come to in a moment. The total number of people, am I losing the right-hand side of the screen?
Nope, you are all still there.
Is my screen on the right-hand side visible to others?
Yes, so we can see the three classes of population.
And then there's a plus between them, and then it says equal N. Can you see the equal N?
Yes, we absolutely can.
Okay, great. Then what I have at the bottom of the screen are the initial conditions. So the Y naught is the people who come in a very, very small number. The X naught is therefore the original number in susceptible. We don't count the Y naught because we want the total to come out to N. And Z naught is the people who have recovered. Well, if nobody's really or have just been infected, they haven't recovered. So Z naught is 0. And X naught is really the total population. Y naught might be, as I said, 5. And for this example, we took N to be 50,000. So the number of infected people who entered the system are 1/100th of 1% of the population of the region, the city, the village, or perhaps even a whole country. And it turns out that the size didn't matter so much. In any case, how do we proceed? Well, we proceed, don't get scared by the equations, look at the top, and you will see that I've got a little handshake emoji. So a fellow from the infected, from those 5 or so infected people that entered into our universe, they go over and they shake hands with as many of the susceptibles as they can, they don't even know what these people had in mind, but they actually wind up pulling them into the infected. And they stay in the infected for a certain amount of time. Eventually they recover. Now, here are the equations, and they're very simple. They are first year calculus. X prime stands for dx dt. It's the derivative of X, means the change in X. And the change in X is that because they are being dragged from susceptible to infected, the change will be negative. X is the number of people that are there, and Y are the number of already infected. And so the product of the two, along with this factor K or kappa, which represents the susceptibility. So in other words, not everybody's going to be that has his hands shaked will necessarily catch the infection, but that number may be very small, maybe 1/10, maybe 1/100th. We'll come to that. And that's the only change that occurs of the susceptible. For the infected, on the other hand, the change, the rate of change or the derivative of y is that same number, except it's a positive number because it's coming in. And a few are going to be recovering. So the recovered lambda, we call the recovery rate, is a multiple of, well, the number of recovered or the number of people who are in there times the recovery rate. Now, typically, it takes somewhere between 15 and 30 days to recover. Dr. Fauci claims that it might have gone down 30%, so it could be as low as 10 days. So lambda is 1 over the number of days, 1/10 or 1/15 or 1/30. Finally, we ask, what's the rate of increase into the recovery? Because it isn't losing anyone. Once they're recovered, they're done. They may not be alive, but they're done. So it is just the number that came out of the infected. So minus lambda y is same lambda y. So these are the three equations, and we will turn them upside down and put them in a mixer and get all sorts of interesting results. By far, well, I use a letter beta for the ratio. It's the number of susceptibles that are being infected divided by the number of people who are recovering. Here is a number which is the magic number. If you know that number, you know how strong the infection is. It's sort of like the Richter scale. You know, the Richter scale of 4, 5, 6, 7. I'm going to give you a lot of results in the very small to the moderately large, using 3.5 as a midpoint of a wide range of guesses of how strong the epidemic is or will be. So this is the basic reproduction number, and keep that R0 in mind. Now, those three equations, as I said, you put them in a mixer and you get a result. Well, the first result you can get by actually dividing the first equation by the third and moving the dz's and the dx's around is this one, which says that we have an equation just in the variable z, which seems like the least important. It's the number that wind up in the recovery room. And it's a regular ordinary differential equation. It has only one weakness, and that's right here. If it were, this is a constant, this is a first degree number. If all we had was the constant in the first degree number, that'd be a first degree ordinary differential equation that describes everything from the discharge of a capacitor to the whatever the losses on the stock market. So the problem is you can't solve this, not in any direct way. So what did the authors do? They did the most logical thing. They used a Taylor series approximation, which is given right here. In our case, x is minus bz. And so using that, only the first three terms, and you'll see why only the first three terms, you get what's called a first order quadratic differential equation. It's also called a Riccati equation for the fellow who first solved one, I guess. And that was a Venetian count named Riccati. So it's also known as a Riccati equation. So it has a solution, and it's pretty monstrous. It involves, well, regular, this is just a constant. This is just another constant, which is given by this formula. And that constant multiplies a a function that you may have possibly never heard of. It's a hyperbolic tangent. But it isn't such a mystery because a hyperbolic tangent is just a difference of exponentials of e to the x minus e to the minus x divided by the sum of the two. So it's reminiscent of the tangent, which is also, except that that is as an e to the ix, and then x is replaced by an imaginary number, and then there's an I down at the bottom. So whether that's pertinent or not, let's go on to the next slide. And here I've simplified it just a little bit. I took out the y0, I took it as 0. Now, of course, that's fiction because if there are no initial infected and infectors, you can't start it. But there's such a small number, it's epsilon. It's, as I said before, if we use the numbers that we put in that formula, 5 in infection initially and almost 50,000 in the population. So that's so small that for all intents and purposes, we can set it to 0 in this formula. And this formula is a little easier to understand because we can look at the hyperbolic tangent, and it's easy to show, if nothing else from the exponential formula, that as t goes to infinity, in other words, as this gets very large, it goes to 1. As it goes to, as it gets very small, well, if it goes negative, this will go negative, but never less than -1. So this argument runs between 0 and 1. Well, what we want to know is what's it going to be? This is the number of recovered people. How many will there be at the end of time? Well, since the end of time, this thing right here, the hyperbolic tangent, has a value of 1. So it's 1 and 1 are 2. And so it's 2 times this. And here I have it. The limit as t goes to infinity is 2 over r naught. And notice everything is stated as in terms of this magic number, r naught, which is n times kappa divided by lambda. There's another formula that we're even more interested in, is how big does the infected pool become? Well, if you recall, the infected pool is in the middle room, and we call it y of t. If I take y of t over n, I mean, in all cases, it's a percentage of the population. So if I look at the number at any given time divided by the number that are by the total population, well, this is the formula, and it's just the derivative of this. So for the math enthusiasts, you know that the derivative of a hypertangent is a hypersecant squared. What's a hypersecant? It looks almost like a Gaussian curve. It looks like a hill. You'll see it in a few slides. And when you square it, it still looks that way. It's a little bit smaller tails. But its value, again, from this formula, it's easy to see that its value never gets above 1. So if that's the case, the maximum, the bracketed term can be is 1. So the total percentage of infected, or the number infected divided by the total population, is just this. So we call the maximum infected percentage is 1/2 times 1 minus 1 over r naught squared. All of this is quite beautiful, except it's not true. So let's go looking for the truth. Well, I talked to you about the little hill. This is a secant, hyperbolic secant square, the blue dotted curve. And it makes sense. Here you're starting your infection. It grows exponentially. It reaches a peak, and then the other part of the formula, the negative exponential, starts coming down. It's actually symmetrical. Now, I said that this wasn't well, it's awfully good approximation to the yellow. But what's the yellow? The yellow is the real world, is the true and correct solution of that equation. Why didn't they do it? We'll come to that later, because they couldn't. Notice this is the horizontal scale is in days. In truth, each number is 3 days. So the truth is that if this were correct, somewhere around 50 days, well, 50, the number 50, which is actually 150 days, unless Dr. Fauci's pronouncement that it's been reduced by 1/3 because of a medication, then it would only be 100 days. Let's hope he's right. This, as I say, is the infected curve, and if you'll believe me that this is in fact the true infected curve, this maximum tells you that you'll get up to roughly 36%. Roughly 1/3 of the people will be infected and will wind up eventually in recovery. Now, the other thing we were looking at was the number in recovery, the percentage that winds up in recovery at the end of time, not in the middle, not at the peak, but at the end of traversing that previous curve. Let me go back to it. That's all of the integral under this curve, essentially, is what I've got on the next one. Right here. And here it's even more dramatic. The Kermack-Kendrick curve is the blue line, and it reaches only 40%, 0.408, as you may notice. And the top curve, which is the true curve, gets up to 0.965. So what a difference. So let's go on to the next slide and see what we can make of it. Well, here, this is a way of condoning or excusing or understanding what the authors originally had in mind using that Taylor series approximation. They had in mind a very, very small number above 1. Incidentally, I should have said at the beginning, if the R0 number is less than 1, the epidemic doesn't even start. So this is just barely enough to get it going. And it's really kind of tiny, because this is the secant squared, and it's a very good approximation to the real world. But notice the peak, the Y max, is only 0.0030, whereas in the other example where R0 was 3.5, we got up to 26% at peak. Well, so this is like 1/100th. It's a very, very weak. And the reason that this is so good is that the Taylor series converges very rapidly in that case. As you go up of the terms in Z, the next term is a very small addition, and on from there. So this certainly validates that what they're doing. It just doesn't apply to a large pandemic. Similarly, this is the curve of the Wait a second. Oh, no, I said something wrong in the previous slide. I said that this is just the peaks. I wasn't talking about the limits. The limit is, is this slide, which again, again, this will get up to not a very large number, under 1/8, 0.12, and the approximation is a very close approximation to it. So, as I said, we would really like to deal with the real curve, but the real curve would have required the solution of a monstrous ordinary differential equation, the one I showed you right at the very, very beginning, which had an exponential in it. So we're not going to be able to do that precisely, but there are 2 points that we can get analytically and accurately with no approximation. And they are the peak, the max, the true max, and the true limit. And if I were to explain this to you, I would be violating what I just promised, no more equations. It's a very relatively simple argument compared to what Kermack and McKendrick had needed for their solution. And it's a relatively simple solution. It says that the peak, the true max, is also a function of R0, but on the surface, very different than the approximate one. But if you make R0 very small, if you make it 1, then everything goes to 0. So you can forget about it. But if you make it very small and you use a Taylor approximation on the log, you wind up with this essentially. And then because it's small, the terms above the quadratic become negligible. Similarly, for the limit of the recovery, where the recovery winds up, this 0.965, is given by this equation. It's not quite as neat. It's transcendental, but it's very easy to solve numerically. And it checks this out perfectly. So let's take a look at the results of both things when in terms of R0. Okay, here's the max, the peak. And the 2 cases we looked at was an R0 of 3.5, and you see there's quite a difference. The approximate gives you 0.26, the true gives you 0.36. On the other hand, the tiny epidemic that had an R0 of 1.1, here you are right down here, and there's curves, you can't distinguish them. Similarly, for the recovered percentage, this is the true at 3.5, it gives you practically 1.965. And for which interestingly enough means that everybody has gone through infection. And all that's left in the bin of the susceptibles is about 4% of the population that was not infected. And again, for the very small one, it's down here, and very few are wind up in the I think it came out to the max was well, it doesn't matter. It was 12%, I think, was where it came out. Okay, now I'm gonna open you up to the truth. We did analytically find the two most important things, the peak of infection and the ultimate recovery. Therefore, everybody who has caught the infection recovered and is in recovery in one form or another. We got those points, but we didn't get the whole curve. So how did we get the whole curve? Easy. We took the differential equations on the first slide and we made them into difference equations. So dx dt, or x prime, we made it into x sub n plus 1, the n plus first sample minus the nth sample. And this is the same as the right-hand side. I just pulled this one over. And then this was the original right-hand side, which was kappa times x. Instead of x of t, we have x sub n and y sub n. And we can make them as close as we like together. And the rest of the equations are that way. And we ran this curve. Well, all it takes in, let's say, 1990s computer technology is to run the iteration. All it takes today is to put it in Mathematica and it wishes right out. But in fact, what Mathematica does is it iterates on this difference equation. You start out with x0 and y0 very small, x0 pretty large. And we get xn plus 1 and yn plus 1 and zn plus 1. And then we do the same with x1, we get x2, y2, and z2, and so forth. So that's what we got. And we got some confidence in that all of this, well, we got confidence by noting that the analytic solution for the endpoints, for the peak and the end of recovery were exactly right. And so we believe this. And then we start looking at things like this. But before we, what this is the infected rate percentage as a function of days or triple days, and for different R naught numbers. So the 3.5, we didn't put the 3.5 in because it would have been too crowded, but it would have been something like this. Well, I should say somewhere between the two. In fact, the peak is at 0.36. So it'll be a peak right here and it'll look just like the other curves. We only went down to 1.5 R naught because if we'd gone to 1.1, you wouldn't even see it. It only picks his head up to 0.03. Now, question, why didn't the authors do this? Well, I can come up at least with two answers. The first is that 19th century mathematicians, early 20th century, wouldn't be caught dead giving you a numerical solution. It had to be something elegant in an equation. And gosh, what's more elegant than a hypertangent and a hypersecant? The other reason that is more logical is they didn't have the means to go through that iteration that either Excel or Mathematica can do in milliseconds, maybe microseconds. It would have taken a room full of data crunchers, and I don't even know if they had mechanical, electromechanical machines like Frieden used to make in the 60s and 70s, which would divide and multiply and make it easy. If they had to do it with a slide rule, well, that wouldn't even be accurate. But so that wasn't at all practical, so you've got to excuse them. However, they did a tremendous, here again, the recovers. Again, this is between 3 and 4, and it's about 0.96. About the green is 4 are not, and the red is 3. So it was somewhere in between, about 2/3 of the way up. So what can we say about all this? Well, okay, we're almost on time. First of all, Kermick and McKendrick proposed a simple logical model. That's what made it so beautiful. They actually proposed several models, including taking account of the age of the susceptibles or the age range. And that never caught on. It was too complicated, too many parameters. And the beauty of it, this is very few parameters. Kappa, the infection rate, lambda, the recovery rate, and the number of people in the group that we're examining. And finally, they're all wrapped up into one, the magic number, the basic, whatever it's called. Okay, what's the principal weakness of the model? And it is a weakness. It's the, aside from that Taylor series mishap, which was perfectly understandable, the weakness is the key parameters, kappa and lambda, that may not remain constant, almost certainly will not remain constant throughout. The lambda, as I said already, they're varying, but it's pretty steady and it's pretty obvious. It's a certain number of days. So that isn't going to, and during the procedure, it isn't going to change much. Kappa may be all over the universe. It can be very large if we get very close together and we have enough infected people. This has been demonstrated. The infection rate may skyrocket. On the other hand, if you do what we're doing, is staying home and communicating through Zoom, or YouTube, then it can be pretty small. So in these curves that we looked at, they may go all over the place. So today it may be down to 2.5, or 2, because we've been keeping our distance. We've been wearing masks, et cetera, et cetera. Tomorrow, everybody goes to work, God forbid, and we climb up to 4 or even higher. In fact, on one talk show, I heard a claim that we're in San Diego, we're already at 5 point something. So the model doesn't cover it. My colleague Roberto has been trying to figure out from real data how the kappa, how the infection rate has changed in various regions, particularly in his almost native Lombardy, which is also my native Lombardy. So let me finish by making a sweeping comment, which is obvious from the beginning. Mathematics is all about creating models. It's a lot of fun for physics, chemistry, and more recently biology. And these folks, Sir Roland Ross and Doctors Kermack and McKendrick have developed some beautiful models. But it's not the real thing. My late mentor and very good friend, Solomon Golom, who should be recognized as, or was recognized as Mr. USC Engineering, had a very interesting view of what you can do with a model. He even wrote a scholarly paper about it. But the story I'm going to tell you here, I don't think was in that paper. He talks about a restaurant. When you walk into a restaurant, you're handed a menu. The menu, if it's reliable, if it's attempted to be what you're going to be served, is a good model for what you'll be served. But please don't eat the menu. Thank you very much for letting me address you, and I'll be glad to take questions. Is there anybody still there?
Yes. Thank you, Andy. There is a lot of clapping that you don't hear, but certainly a lot of people appreciated and enjoyed your presentation. We have received a number of questions, and so I'd like to go through some of them. I think we have received, I don't know, maybe 60 questions, so I have to sort of triage them. One question that is one theme that is common between all the questions is the following. How can engineers better work with healthcare professionals and politicians to identify scalable solutions to pandemics?
I'm sorry, I didn't understand which engineer is he talking about?
Simply engineering professionals that can work with health authorities and politicians or policymakers to make sure that we address pandemics and solutions in a more, I suppose, enlightened way.
He wants me to identify such a person?
No. How can this happen?
What's that?
How can this happen? How
can this happen?
Yeah.
Well, the U.S. Congress is a body of, I think, 538 people. It's conceivable, well, I'm sure, and I know there's at least 2 engineers among them. So maybe we can get to them and they can try and maybe they'll even pass a resolution.
Yes. One question that I was able to answer in the chat is why are the recovered population, what is the recovered population, also include the dead people? And the assumption I assume is that one could potentially put a mortality rate there and then separate the ones that die versus the ones that survive. I suppose that's the answer, correct, Andy?
Well, exactly. I had no way of, and I dare say neither did the authors of that paper. There's a lot of conditions and age and so forth and so on. And maybe that's what they were trying to identify in a more elaborate model. But certainly beyond my pay grade.
Right. I suppose one could potentially include in the model the capacity of hospitals to deal with sick patients. And therefore, after a certain point, the mortality rate increases because of the incapacity of the hospital. And therefore, they need to flatten the curve.
There was a paper written just 6 years ago by 3 mathematicians, actually, one in England, in London, one in Portugal, and one in China, Hong Kong. And they amplified the model to include deaths, which were both deaths due to the pandemic and those not due. And but in order to do that and make their model stable, they had to have a number of births exactly equal to the number of deaths. And I haven't played with those equations, but it could be an interesting exercise for the student.
Thank you. There's a question by, I think, a current PhD student. It's more of a mentoring question. How would you prepare for a post-coronavirus world if you were a current PhD student?
If you were what?
If you are a PhD student today, how would you prepare for a universe in the post-coronavirus era?
Well, make the best of it. if you're already working on your dissertation, spend more time on it. Talk to your advisor. He doesn't have anything to do either. Right, Yannis? Pardon.
I don't know if he's our PhD student or not. I think he is at this particular case.
So, yeah, well, just speaking for myself and maybe for Roberto, we had a great time working on this. I just happened to come at the right time, and normally we probably would have been too busy with any number of things to even consider it. So make good use of your time is all I can say.
Wonderful. There's a question which I think I can answer perhaps, or maybe you will help us answer that as well. Do you think that the Viterbi School of Engineering will play a part in preventing future epidemics?
Could I?
Would the School of Engineering, our school, play a part to prevent future epidemics?
Could they pay?
Play.
Play. Oh,
Play
what play? Oh, play. Could, yeah, I understand. Sorry. Well,
I can help you.
Education, well, first of all, clearly, as much as I love mathematics, biology is the queen in more ways than one. And here it's absolutely. So make your, I would imagine that in future academic years, there will be more courses that deal with infection and the effects on society.
There is a number of our faculty who are already working on related topics. We have a faculty member who is working on vaccines for the particular coronavirus situation. We believe that computer science is going to be play a very big role in partnership with biology, from AI to machine learning, big data, and all that. And we're preparing for obviously for these types as well.
As you say, Yannis, as you say, it's engineering plus.
There you go.
Plus is everything, right?
Well, thank you for the advertisement and the endorsement. That's great. I will read one more question, and perhaps one question is, if you could tell us a little bit about how one can generate herd immunity, which is something that has been, proposed as a way to essentially go and continue living our life as we used to. The concept of herd immunity.
Oh, herd, yes, a very good point. I meant to say it. In the case, the analysis or the calculation for the R naught, for the pandemic with an R naught of 3.5, we got almost to herd immunity because all but 4% had gone through it. Now, in Sweden, as many of us have heard, the authority, the equivalent of Dr. Fauci, said, let's go for it. Let's go for herd because it'll happen anyway. I think he's backed away from it to some degree, but the fact that it may well happen, the only thing that can prevent it from going up and up is a vaccine, and that'll take time.
Absolutely. Yeah. Yeah, that's absolutely the case. I think we are at the end of our allotted time. I don't want to abuse the time of other people. Andy, we thank you very much for showing and giving this excellent presentation. It is amazing that if we were to do this in the previous universe, we would have to bring people on campus, find a classroom, an auditorium, and go through all these things. Right now, we can do this with a notice. I want to tell the audience that you suggested this idea no longer than like 6 days ago. And we decided to do it. And look, we have more than 500 people that attended it. And it's a wonderful thing to do. Thank you so much.
I would
very
just
much
like to
appreciate it.
add, I'd just like to add that this work was jointly done with Roberto Padovani, and we egged each other on.
Yes.
To get.
Thank you to Roberto as well, good friend of the school, very much appreciated. So back to you, Tiffany.
Thank you so much, Dean Yortsos. Thank you so much, Dr. Viterbi. This was amazing. We had so many people tuning in here and live on YouTube. This was truly an exceptional event. May I please ask that you actually turn your cameras off as we excuse everyone else, and we will continue the conversation. And to everyone else who tuned in today, thank you so much, and fight on.
Right on.